Lesson 42, Virtual Member Functions. To follow along with this lesson, you will need to create a new console project and add a new file named main.cpp to it, as we did in Lesson 1. This lesson introduces one of the most fundamental notions of object-oriented programming, polymorphism. Our first program contains a base class and a derived class that inherits it. These classes contain two member functions, one is virtual and the other is not. These functions print a simple message that tells which class the function was called from and which function was called. The virtual function is said to be overridden by the function in the derived class, and we will show exactly what this means in this program. In our main function, we instantiate a base object and a derived object. Then we declare a base pointer and a derived pointer. Below this, we set the base pointer to point to the base object and call our member functions through the pointer. Then we set the derived pointer to point to the derived object and call our member functions through it. Lastly, we set the base pointer to point to the derived object and call our member functions through that. Executing the program, we see that the first two cases are straightforward. If we point the base pointer to a base object, we call the base functions. If we point the derived pointer to the derived object, we call the derived functions. In the third case, where we point the base pointer to the derived object, the base member function is called for the non-virtual function, and the derived member function is called for the virtual function. This illustrates what we mean when we say the virtual function is overridden. It isn't clear at this point why overriding functions is useful, but this second program should give an indication of the power of polymorphism. In this program, we have a base class named shape with a virtual member function named area. Since the area of a general shape is not well defined, this function just returns 0. This function is overridden in the derived classes circle and square, where the functions for calculating the areas for those shapes is used. In our main function, we create an array of 5 shape pointers. Then we create 3 circle and 2 square objects and set the elements in our array of pointers to point to them. Then we run a loop to cycle through the array and call the area function on each pointer. What we have done here is to use the shape interface to make all of our objects that are in the array look the same from the user's perspective. However, the area computation acts differently depending on the type of the object that the pointer points to. Polymorphism means to have many forms. In this case, the shape literally takes on multiple forms, a circle or a square. We said before that the shape area function returns 0 because the area of a generalized shape is not well defined. It would be better if we just didn't allow programmers to create shape objects at all. To do this, we can make our area function in the shape class a pure virtual function by setting it to 0 like this. Putting a pure virtual function in a class disables objects of that type from being created. However, we can still use the pointers of that type, just as we did before. In fact, we can compile and execute our code just as before with the same result. We can think of a pure virtual function as being like a member function pointer. Depending on the object type, the pointer points to a different function. This program gives a more sophisticated demonstration. In this example, our base class is a car class with a single pure virtual function. The class Ford inherits car and implements the print, make, and model function. The class Ford also has a print, make, and pure virtual function print model. The classes Ford Taurus and Ford Mustang inherit the class Ford and implement the virtual function print model. The class hierarchy looks like this. The classes Ford and car have pure virtual functions, so they cannot be instantiated. For this reason, any class with a pure virtual function is called abstract. If a class has only pure virtual functions and no data members, like the car class or a previous shape class, we call it an interface. In our main function, we instantiate a Ford Taurus and a Ford Mustang. Then we declare a car pointer and point it to each of these and call the print, make, and model function. Executing the program gives exactly what we would want. However, the code is tricky, and it is important to look it over carefully to make sure it makes sense. For our last example, we demonstrate why it is sometimes important to make a destructor virtual. Here we have a simple base class with a simple constructor and destructor, and a derived class with a dynamic allocation and deallocation in the constructor and destructor. In our main function, we declare a base pointer and assign it to a dynamically allocated derived object. Then we delete the pointer to deallocate our dynamic allocation. Executing the program, we see that the base constructor and destructor were called, as well as the derived constructor. However, the derived destructor was never called, and the double that was allocated in the derived class was never deallocated, so we have a memory leak. To fix this, we make the destructor virtual. Now if we compile and execute the program, we see that the memory is deallocated. This concludes the lesson.